Let's go into ANSYS Fluent proper now and talk about the technology there. So improvements for parallel. Work had been done previously, as you know, on CHT scale-up. This is being made default now when you're doing the automatic partitioning. Improvements to sliding mesh scalability. Improvements to the DPM mesh parallelization when you've got features active that prevented it before. So there's now a new quick search command so that you can go and search for keywords. So those could either be keywords from the tree or in the TUI, and it now makes analyzing and finding stuff in a complex model much easier. Last release we presented the VOF to DPM model. So the idea here is that you can do very detailed VOF modeling, say of droplet formation from spray breakup, but at the end, once you've got small enough droplets and they become spherical, you actually want to be able to model those using DPM. Well, you could transition to that previously, but there was a significant amount of work needed. Now you can start recording an injection file essentially and doing that automatically. There's also a new breakup model which is available for a jet in a crossflow. The Eulerian wall film can now deal with partial wetting, so you can see some very realistic looking flows in these two simulations. What happens when you have a partially wetting surface. There's been a lot done in combustion, particularly around improvements with the speed of calculation of flamelet libraries, creating the source term for FMG, lots more access via user-defined functions. But the thing I want to actually concentrate on here is that we know the Chemkin solver was integrated into Fluent, but it was not a full integration. When you use Chemkin, you weren't necessarily picking up the properties data that the Chemkin file was providing. Now that has all been implemented fully so that you've got a consistency across Chemkin simulations and Chemkin simulations in Fluent. There's also controlling parameters now to allow you to use dynamic cell clustering with a lot more control. And for those doing surface reactions, the hfcov command from Chemkin, which allows you to have enthalpy coverage dependence on composition, has now been implemented. Overset meshes continue to become very popular and have more and more work done on them. So they're now supported for compressible flow with both the pressure and density based solvers. And then there's a whole range of general improvements here to improve surface integrals, to allow you to inject fluid into a component mesh, to improve the transitions from dead to solved cells. Mesh adaption, the new Puma scheme, which allows very good transient adaption, can, under certain circumstances, allow you to create rather poor quality cells. You can now prevent that with a TUI command. And there's a new stabilization scheme which can be applied when you're using dynamic meshes and you're either using diffusion-based smoothing or the linear elastic solid smoothing. GMRes can be used to stabilize the solution. There's work done to improve the robustness of non-conformal interfaces, making it less likely that you would have to use the mapped option now. Better convergence and setup for hybrid initialization. So when you've got different boundary conditions, you need to extract information from them to do this setup. That's being done better now. And also some of the warts that you had before, like this wiggle at an exit boundary, have been removed. So you're getting a much cleaner start to your solution. Multiphase is a continuing drive for improvements. One of the big features is the ability to use a non-iterative solver, a NITA solver, for multiphase flows. That required a lot of tweaking in the past. Now they've come up with a set of under relaxation factors that make this much easier to do. There's improvements to the body force weighted pressure discretization, which means it can be superior now when you're working with NETA to the Presto scheme. And you can see here Presto was diverging. There's also work to improve Presto, particularly when you have a non-orthogonal mesh. There have been other multiphase improvements, particularly around usability, moving the evaporation condensation setup into the phase interaction box where it belongs, being able to use a new drag law here, the Ishizuba model, which CFX users find really beneficial, and some improved numerical treatments in cavitating flow and VOF, and some new output variables for post-processing. So, moving on to turbulence, when you want to link, say, a RAN scheme to a large eddy region, you need to generate synthetic turbulence. That's now being done much better at a lower cost, and you're now able to address the parameter in the curvature correction. So if you're applying curvature correction to capture swirl, you can now access the C-curve parameter. There's improvements to the graphics, a new vector arrow, smoother contours. Something that I really appreciate and have used, that when you've got a steady state run that doesn't quite converge, you'd like to avoid running a transient, so you can switch on steady statistics, and from that you can compute a mean and a root mean squared error, so you can see where is the flow settled down, where is it varying, and what's the size of that variation. That's a welcome addition. System coupling. There's now support for data exchange on polyhedral faces, which wasn't there before, and it's now using the system coupling 2 framework, which allows you to generate scripts and that. And this is also true for CFX. Reduced order modeling. The idea here is that you can use the ROM builder, which has been added into Workbench, to generate a much simpler model of a process so that you can run very quickly. And you might want to use that standalone, or you might want to feed that ROM into building a digital twin for your whole device. So here we've got an example around corrosion. So we've got a pipe here. We've got potentially different flow rates, different temperatures, different pHs. There's a electrochemical reaction where carbonic acid is creating corrosion. And we'd like to be able to know the rates of corrosion, etc., for any parameters within that range. So how do we do it? We set up a full CFD simulation of this corroding flow here, and after 30 simulations, there's a trained ROM here. The difference with it, though, is that each CFD simulation requires an hour's CPU on 12 cores, and now this ROM runs on just about anything in a couple of seconds, and results are very close. So it's a way of being able to simplify data and use it very, very quickly. Adjoints are continuing to be exploited. The adjoint solver for shape optimization. So there's new boundary conditions for mass flow outlets and pressure at the far field that are supported. You can now use total temperature in integrals, and your volume integrals can be not only over a zone or a box, but you can now use any region you can set up with a cell register. Also, the numerics have undergone considerable improvement. We know that these are pretty nasty equations to solve. There's new stabilization methods to help you get convergence much faster.